Let's come to oxidation state. And as we discussed in electronic configuration, certain systems which were either empty, half filled, or completely filled. So those systems will now work here in explaining oxidation state of lanthanides. So most of lanthanides have been found to exist in +2, +3, and +4 oxidation states. And these states are not uniformly occurring in case of their complexes, in terms of their complexes. +2 oxidation state theoretically can be drawn for all lanthanides, but some +2 systems will be very stable and some +2 system will be unstable. But if the compound exists, so this compound we have to explain on the other of certain other factors which exist in the complex or in that oxidation state, or which are responsible for stability of oxidation state of lanthanides and +2. +3 is very common oxidation state, and all lanthanides exists in +3 oxidation state. There are certain lanthanides which also exist in +4 oxidation state, and this +4 has been observed for only 4 systems. One is cerium, the other one is praseodymium, third one is terbium, and fourth one is dysprosium. Once again, I have marked two systems, two elements or two electronic configuration by red, and this red means they violate electronic configuration rules. But electronic configuration rules, as I told you, somehow we are able to explain them, and in some places we are unable to explain them. So the table is the overall table indicates that common oxidation state of lanthanide is +3. There are two systems with +4 oxidation state. They are cerium and terbium, and there are two which are more stable, and europium +2 oxidation state is europium and ytterbium. So if you look where europium is, where ytterbium is, why they are stable in +2 oxidation state. So look at europium. So the oxidation state in +2 is 4F7, and because of this F7 the system is extra stable, as we discussed that this is a half-filled electronic configuration. Then ytterbium is second last in the series, and this possesses 4F14 electronic configuration. Since 4F is completely filled, therefore the system is extra stable. In case of oxidation state +4, cerium is stable. So cerium and +4 oxidation state is stable because it has no electrons in any of these three shells. Therefore this is stable system. Or the anti-penultimate shell possesses 0 electrons, therefore the system is extra stable, and its stability can logically be explained on the basis of electronic configuration rules. Then terbium possesses +4 oxidation state. So if you look at terbium, so terbium will also have certain electronic configuration. So this is terbium, and coming to its electronic configuration, it has 4F7 electronic configuration, where F is half filled and is regarded as extra stable in the series. So these are some points of interest which can be considered, and you should be able to explain them. In a summary, again, let's cut it short. So +3 is very common, and +2 and +4 are stable in F0, 7, and 14 systems. +2 ions for europium and ytterbium are well explainable. For +4 can be explained for cerium and terbium. +3 extra stable systems are lanthanum, gadolinium, and lutetium. And please refer back to electronic configuration of these systems in +3. So lanthanum possesses F0 system, gadolinium is F7 system, lutetium is F14 system, and on the basis of 0, 7, and F14 they can be explained that why they are extra stable. So existence of some systems cannot be justified, and these can be regarded as violation of the rule. Samarium +2 and thulium plus 2, praseodymium plus 4, and neodymium plus 4. So general rules cannot justify these oxidation states, but as I told you, rest of the factors have to be taken on board for explaining these oxidation states. So magnetic properties of lanthanides. They are generally associated with unpaired electrons present in F subshell of respective lanthanide ion. All lanthanides which have unpaired electrons would be regarded as paramagnetic, and those with no electrons in F subshell or with paired electrons in F subshell, they will be diamagnetic. So, in case of lanthanides, some members are diamagnetic. For example, the lanthanum plus 3 is diamagnetic. Lutetium plus 3 is diamagnetic. Ytterbium and cerium plus 4, they are diamagnetic. So three elements in the series in plus 3 oxidation state and 1 in plus 4 oxidation state, they are diamagnetic. And if you look into electronic configuration of these ions and you go back to the table where we have already discussed the oxidation states of lanthanides, so they will either have zero electrons in their valence shell, in their valence not valence shell but F antipenultimate subshell, or will have paired number of electrons in the respective shell. Therefore, they will show no magnetic properties. Now, in order to theoretically determine magnetic properties of compounds or isolated ions, this formula is generally in use where n into n plus 2 under the root. This is the number of n represents the number of unpaired electrons, and the overall formula is called spin only formula. In this case, where the formula is applicable, we can determine theoretically the magnetic properties of those species where unpaired electrons are known, and normally the experimental and theoretical calculations are matchable with each other. Now, in case of lanthanides, if we use the same formula, so this formula is of no use. Therefore, another formula has been introduced for the system in order to predict the magnetic properties of lanthanides, and this formula is 4s into s plus 1 plus L into L plus 1 under the root. Here, two factors are involved in determining the magnetic properties of lanthanides. One is spin and the other one is orbit. So orbital angular momentum and spin angular momentum, both of them contribute almost equally in determining magnetic properties of lanthanides. And this is a specialized formula used for lanthanides and uh, in coming chapter or series of compounds, that is actinides. In this case, spin quantum number and orbital quantum number we have to know. We should know about them, that what is spin quantum number, what is orbital quantum number, and in some books you will also find the formula a little bit more complicated with some other factors, where the factor J or some others are introduced after the orbital get more than half filled in terms of electrons. So as we discussed, lanthanum plus 3, this is 4f0 system, and definitely when there are no electrons, so the system will show no magnetism and it will be diamagnetic. In the series, neodymium shows maximum magnetic properties with number of unpaired electrons, which is also maximum. So this is the ion with maximum number of magnetic properties. For samarium, the magnetic properties decreases to 1.5 and from samarium again the magnetic property starts rising, and for dysprosium and holmium the properties are on the top are maximum in the series, and then again the properties decreases, and it comes to zero or drops to zero for lutetium, where the electronic configuration of lutetium plus 3 ion is well uh, explainable on the basis of this zero magnetic properties for the system. Let this is a table where the magnetic properties of lanthanides are given and taken from the book which I have already handed over to you. So the properties, if you look, they increase gradually, and this is in first half. In first half, or not in first part, these two are the maximum values obtained for these two metal ions, and the properties are for lanthanides in +3 state. Then the properties for samarium is it decreases, and for europium again increase start and reaches to 10.4 and 10.3, which is maximum in the series for dysprosium and holmium, and again it drops and reaches 0 for lutetium. So this is the graph representing the magnetic properties of lanthanides, and you can say that in lanthanides there are two species. In the beginning of the series there are two elements which have maximum properties, magnetic properties, then decrease in properties, and again increase in properties, and maximum value has been attained for dysprosium, closer value for holmium, and then the minimum value for lutetium, and at this end for lanthanum, and both these systems possess no unpaired electron in their atomic structure or in their ionic structure, therefore they are diamagnetic. Then lanthanides contraction. So the series, this graph has been designed for lanthanides in +3 oxidation state, and in these lanthanides ions, the top one is lanthanum, and at the bottom this is lutetium. So for top one the value is 116 picometer, and for the lowest this is 98 picometer. If you look at the change, so change is gradual almost, and this gradual change in decrease in ionic or atomic size of lanthanide is called lanthanide contraction. Why the change is gradual, why there is not big difference between lanthanum and lutetium in terms of their sizes? So this is special characteristic of lanthanides, and that is why this characteristic, this property is prominent for this series of elements, not for rest of the periodic table, and this is because of imperfect shielding of incoming electron in F subshell, which does not affect the system too much. So the change is gradual, and there is not too much difference between two extremes of the series. There are certain properties which can be explained on the basis of this lanthanides contraction, which in other words we can say the gradual decrease in size. Electronegativity of the series for trivalent ions, it also changes gradually. So if you uh, consider the electronegativity in the series, so you will find very small difference between lanthanum and lutetium at two extremes of the series. Then basicity of the systems for hydroxy bases can be explained on the basis of this change, that is lanthanide contraction. So bases, yeah, hydroxide on one extreme are more basic, and on the other are least basic. So, and this less and maximum and minimum basicity can be linked with covalent characters. So on one hand side covalent characters will be maximum, and